The equation for simple harmonic motion. With a simple harmonic motion, you have a equilibrium position here, and so you can displace the object from the equilibrium position up or down and go back again. So you can go back and forth open. So you can have a vertical displacement and horizontal displacement. When you have a displacement, you would have the y vertical displacement, which is your y, and x displacement. So if you going up in one direction or along the x-axis, you're generating a circular motion. So it doesn't matter which way you're going, you're generating a circular motion. And let's assume this is your point here, point x and y, and that point would generate an angle, that point on the circumference, an angle theta, and this angle theta will have the y value, this is the y, and it will have the x value, that's your x, and the radius r. So we can write Cartesian coordinate, which are x and y, well, which is x and y, because that's the only point we got here. And now we need to write these in the polar coordinate. And to do that, we would have to use, because we've got right angle triangle here, so what we have to do is to use something called SOHCAHTOA. So I'm going to use SOHCAHTOA, and with the SOHCAHTOA we've got basically sine of an angle theta is opposite over hypotenuse. So that's opposite and hypotenuse. At the same time, we got the cosine, the complementary of sine theta, which will be adjacent over hypotenuse. And then we also have the tangent, which is tangent of theta is opposite over adjacent. So we can do sine of theta will be equal to y over r. So sine is opposite over hypotenuse. So that's what sine. Then we can write the y by multiplying both sides by r. So that would be r sine theta. We can also write the x by doing cos of an angle theta would be, the cos is adjacent over hypotenuse, so that will be x over r, and therefore multiplying both sides by r, we get x equals r cos theta. When r equals 1, you would get, if we put r equals 1, so y would be sine theta. And if r equals 1, x will be cos theta. And so now you can see the polar coordinates for x will be cos theta, and for y will be sine theta. So the vertical movement here is describing the sine, and the horizontal movement is describing the cosines. Use the x equals r cos theta for the displacement. We could use y, but we'll just use the x in this case. So for the x equals to r cos theta, that will be the angle of, that will be the displacement. So the displacement here is going to be x equals r cos theta. We could use y displacement of equals r sine theta as well. It will be similar. But when it displaces to its maximum, the maximum here is going to be the value on the maximum here will be a. So that will be x equals a here, and x equals minus a. So this is minus x. So that will be x equals minus a and x equals a. And if you're doing the displacement in the y direction, that will be minus a here, and that will be plus a. So you can see at the maximum displacement, r equals a. And when r equals a, then you're going to get x equals a cos theta. So this is the displacement that we have. So we can now sketch the graph of this. But before we do that, we know that the angular velocity is actually angular displacement over time. So that's angular displacement over time. So this angular displacement over time. Now we can write the angular displacement will be equal to omega t. This is the angular velocity, and that's angular displacement, and that's time. So omega is angular velocity. So if I write it here, angular velocity is that's angular velocity. Or you might call it, in this case, you might call it angular frequency as well. And the unit for that is radian over seconds, which is rad per second. So that'll be unit. For, as you know, the linear velocity is linear displacement over time. Just to write that down, if you want to do linear velocity, v, that's linear velocity will be linear displacement over time. So you can see it's easier to remember angular velocity will be angular displacement over time. Now, as I said, I'm going to now replace angular displacement here with the omega t. So therefore, x would then become a cos omega t displacement that we have for simple harmonic motion. And to sketch the graph, you'll be plotting x against time. So using cos, so you can see when we are sketching the graph, and cos starts from there, and it will go from there to pi. This is time t, and this one here is x. So that will be from 0 to pi over 2, and from pi over 2 in time, by the way, will be going all the way to, and so it's continuous. So that's when t equal to 0. And you can see the maximum displacement here will be plus a, that a over there, and the minimum displacement here will be minus a. So one need to remember that you're plotting x against t, and then this is for when pi over 2, this is this point here is pi, and that point here is 3 pi over 2, and this point here is 2 pi of time t. Right. So we need to remember that the angular displacement is a cos omega t, and when t is 0, as you can see, at t equal to 0, you're going to get the cos. When t equal to 0, you're going to get x equals a cos omega t, omega times 0, and that would be, in fact, you're going to get plus or minus a. So when t equal to 0, at t equal to 0, your omega will be plus, x will be plus or minus a when t equal to 0. So that's the maximum displacement at plus a. So therefore, x equals a when t equal to 0. And a is measured in meters. And a is measured in meters. A is the amplitude, which is the maximum displacement in meters. And t is in seconds, time in seconds.